Close your eyes and drift back in time far, far back. Not just centuries or even millions of years, but billions. Imagine the Earth more than 2.5 billion years ago. It was the same planet, but an entirely different world. The air that surrounds you now, full of oxygen that fills your lungs with every breath, did not yet exist. Instead, the sky was dense with other gases, methane, carbon dioxide, and nitrogen. The atmosphere was heavy, its chemistry unfamiliar to us, yet perfectly suited to the forms of life that quietly thrived at the time. If you could stand on the surface then, the sky might not have appeared blue as it does today. Instead, the methane and haze could have given it an orange, reddish, or even brownish hue, dim and surreal beneath the young sun. The sun itself was weaker, glowing only about 70% as strongly as it does in our own age. And yet, despite the faintness of its rays, Earth's oceans did not freeze. Methane, a powerful greenhouse gas, trapped heat in the atmosphere, keeping the seas liquid. Those oceans stretched across much of the planet, vast and deep, but alien in their chemistry. They were rich in dissolved iron, giving the waters a strange quality. No fish swam in those seas, no corals built reefs, no plants swayed in shallow bays. The oceans were alive, but only in ways invisible to the human eye. Their tiny microbial cells drifted and multiplied. They clung to rocks, coated the sea floor, and built strange layered mounds called stromatolites. Stone-like structures created over time by mats of bacteria. These humble creatures were the architects of the first ecosystems. Their world was slow, quiet, and patient, measured not in years or centuries, but in the steady accumulation of life's microscopic activity. On the continents, Earth's land looked stark and barren. There were no forests, no grasses, no flowering plants. Instead, the continents were dark with volcanic rock, slowly weathering under rain and wind. Small patches of shallow soil may have existed, but they were lifeless. The land was empty, a silent stage, waiting for actors that would not appear for billions of years. And yet, life was there. In the oceans, life had been present for more than 1 billion years already, though in its simplest forms. Single-celled organisms had learned to use chemistry to power themselves, feeding on what was available in their environment. Some of them thrived by breaking down methane, others by using sulfur or iron. They lived without oxygen because oxygen was not yet part of their world. In fact, to them oxygen was not a friend at all. It was a reactive, dangerous gas, capable of damaging the delicate machinery of their cells. This was a planet in balance, a balance unfamiliar to us, yet stable in its own way. The Earth was warm enough for water to flow and oceans to remain liquid. The microbes that filled those oceans lived in a harmony suited to their needs. There was no hint yet that everything was about to change. But change was stirring. Some of those tiny microbes were unlike the others. They had discovered a remarkable way to harness energy through photosynthesis. By using sunlight, they could split water molecules and release oxygen as a byproduct. To us, oxygen is essential. To them, it was simply waste. Invisible bubbles of oxygen began to trickle into the surrounding seas, an almost imperceptible change in the chemistry of the ocean. For millions of years, this oxygen did not accumulate in the atmosphere. The iron dissolved and the oceans absorbed it, turning into rust that sank to the sea floor. Layer by layer, iron oxides were deposited, forming what we now see in ancient rocks called banded iron formations. These rocks are Earth's diary, silent witnesses to the earliest whispers of oxygen. Still, the atmosphere remained unchanged. The oxygen never lingered long enough to escape into the air. The Earth above the waves went on as it always had, a lifeless volcanic land beneath an alien sky, and yet the process continued. The microbes did not stop. They multiplied, covering vast stretches of shallow seas, tirelessly producing oxygen. They had no concept of what they were doing, no sense that they were altering the planet forever. To them it was simply survival, but to Earth it was transformation in slow motion. Imagine drifting over that ancient world, the seas below teeming with invisible life, the continents dark and quiet, dotted with volcanoes releasing gases into the thick air. The sky tinted strange colors lit by a weaker sun, and within the oceans, countless tiny cells carrying out their silent work. Work that would change the world more profoundly than any event before or since. This was the threshold, the moment just before oxygen began to rise, the calm before an invisible storm. Earth was on the edge of an epochal transformation, though nothing on its surface revealed the magnitude of what was coming. In this stillness, we see the beauty of deep time. Billions of years ago, life was simple. The planet was quiet, and yet, in the smallest of cells, a revolution was beginning. One that would fill the air with oxygen, reshape the climate, wipe out much of life, and set the stage for everything that followed. This was Earth before the breath of oxygen. A planet alive, but poised on the edge of change. A change that would mark the beginning of a new world. Before the world filled with oxygen, Earth's atmosphere was ruled by other gases. To us, they might seem unbreathable, even toxic. But for the earliest life, they were the foundations of existence. Imagine standing on a coastline 2.7 billion years ago. The air is heavy, carrying the faint tang of volcanic gases. If you could test the atmosphere, you would find almost no oxygen at all. Instead, the sky is thick with methane, carbon dioxide, and nitrogen. Together, they weave a protective blanket around the planet, keeping it warm under a sun that was still weak. Methane, in particular, was a quiet ruler. It is a greenhouse gas far more powerful than carbon dioxide. Even in small amounts, it traps heat. In the young Earth skies, methane was present in abundance, produced by ancient microbes known as methanogens. These tiny organisms thrived in the oxygen-free world. They fed on hydrogen and carbon compounds, releasing methane as waste. Over millions of years, their activity filled the atmosphere with enough methane to counteract the faint young sun. Carbon dioxide played its role too. Volcanoes, ever active, belched vast clouds of CO into the skies. This carbon dioxide mingled with methane and nitrogen, creating a dynamic mix of gases. Rainfall slowly drew some CO down, combining with rocks to form carbonates. But the balance remained. Earth's climate, though fragile, was stable enough for oceans to stay liquid, for life to persist, and for the cycle to continue. The air would not have been pleasant. Breathing it would have been impossible for us. But to the early microbes, this was paradise. An aerobic life, life that flourishes without oxygen, reigned supreme. These organisms had evolved in harmony with methane and carbon dioxide. To them, oxygen was an intruder, a threat, and in this ancient world oxygen was almost entirely absent. The sky itself may have been different in color. Methane, when combined with sunlight, can create a thick haze of organic particles. It is likely that the Earth's atmosphere had a smoggy, orange-brown tint, not unlike the hazy sky of Saturn's moon Titan today. Under this alien canopy, the sun's rays filtered dimly, giving the planet a muted glow. The haze may even have offered protection, shielding the surface from harmful ultraviolet radiation that the young planet was otherwise vulnerable to. This balance of gases shaped not only the climate but also the chemistry of the oceans. The seas were rich in dissolved iron, giving them a greenish, sometimes reddish appearance. When methane bubbled from microbial mats on the seafloor, it may have drifted upward in shimmering plumes, like ghostly lanterns rising through the water. Carbon dioxide dissolved readily in the oceans too, making them slightly acidic. This acidity influenced how minerals formed, how nutrients cycled, and how early microbial communities survived. To the tiny organisms of the time, this was the normal state of the world. There had been no other. Generations upon generations of microbes lived and died under methane-rich skies, in oceans filled with iron, on continents barren and volcanic. The rhythm of life was slow but steady. It is worth pausing here to think about the fragility of this balance. The Earth's climate system was already a delicate dance. The weak sun, the greenhouse blanket of methane and the recycling of gases through microbes and volcanoes, all of these factors combined to keep Earth habitable. Remove methane, and the planet might have frozen solid. Remove carbon dioxide, and the seas might have turned too acidic, dissolving the very rocks that anchored the continents. This was an early Earth held in a tenuous equilibrium. And yet, even in this balance, subtle changes were underway. Not all microbes were methanogens. Some were experimenting with a new kind of chemistry, photosynthesis. They harnessed sunlight not just to survive, but to produce energy in a radically different way. And in doing so, they created a byproduct that the methane-rich world was not ready for: oxygen. For now, oxygen remained trapped, reacting with the iron in the oceans and never accumulating in the air. But every molecule released chipped away, ever so slightly, at the methane-dominated sky. Over millions of years, this quiet process would destabilize the balance that had kept Earth warm and hazy. And when it tipped, the change would be global. But at this stage, in Chapter 2 of Earth's oxygen story, methane and carbon dioxide still ruled. The haze still blanketed the planet. The microbes that produced methane still thrived, unaware of the revolution being set in motion. Imagine again that coastline, with waves lapping at dark volcanic rock. The air is thick, tinted by the faint haze of hydrocarbons. The sun glows dimly, weak and filtered, but the world is warm enough for the seas to move and for life to grow. It is a planet that feels both familiar and utterly alien. This was Earth in the time before oxygen, a world ruled by gases that today we call pollutants, a world whose stability depended on methane's invisible hand, and a world standing on the edge of an unseen transformation, the kind that only billions of years could deliver. The dominance of methane and carbon dioxide would not last. Already, in the shallow oceans, the quiet work of photosynthesis was beginning to unravel the balance, and soon Earth would change, in ways that life could not anticipate, and from which there was no return. Drift with me now into the shallow seas of the early Earth, more than 2.5 billion years ago. The water is warm, tinged with green from dissolved iron, and the seafloor is coated in soft microbial mats. Here, in the quiet shallows, some of the most extraordinary pioneers in the history of life are at work. The cyanobacteria. They are tiny, smaller than the width of a human hair. To the naked eye, they are invisible, but under the microscope of imagination, their world comes alive. Cyanobacteria are single-celled organisms, drifting together in colonies. They shimmer faintly with pigment, not just chlorophyll, the green molecule we know so well, but also shades of blue and red. It is this coloring that gives them their name, cyanobacteria, the blue-green bacteria. What makes them remarkable is their talent. They are the first life forms we know of to use water and sunlight to create energy, through a process we now call oxygenic photosynthesis. Using the gentle power of light, they split molecules of water apart. In doing so, they draw energy to build sugars, the building blocks of life, and in the process, they release a by-product oxygen. At first, this oxygen had no place to go. It reacted immediately with the vast amounts of iron dissolved in the oceans. The oxygen combined with iron to form rust, which sank and settled, layering itself into banded iron formations. If you look at certain ancient rocks today, striped with red and gray bands, you are gazing at the fossil signature of these first cyanobacteria. Their microscopic labor, repeated for millions of years, etched its presence into the very crust of the earth. But the cyanobacteria did not know the scale of what they were beginning. For them, oxygen was not a goal, merely a consequence. They were simply surviving, finding their niche under the sun. And yet, by releasing oxygen, they were slowly preparing the atmosphere for a transformation no life had yet experienced. Picture them drifting in colonies just beneath the surface. The sunlight above nourishes them. As they grow, they form thin films on rocks and sand, or they stack into living layers that trap sediments and build strange structures called stromatolites. These mounded, stone-like towers dotted the shallow seas, some growing meters tall. In places they created entire reef-like systems alive with microbial activity. Stromatolites still exist today, in rare corners of the world such as Shark Bay in Australia. When you look at them, you are seeing one of the oldest living forms of architecture on Earth. Each layer in their domed structures is built by cyanobacteria, just as they did billions of years ago. They are not only survivors, they are storytellers, preserving the memory of Earth's earliest oxygen factories. For the world around them, the cyanobacteria were both creators and disruptors. Their oxygen began to strip away the methane haze that had long blanketed the skies. With less methane to trap heat, the Earth slowly cooled. Some scientists believe that this cooling may have helped trigger ancient glaciations, perhaps even global, snowball, events that covered the planet in ice. In this sense, the cyanobacteria were climate engineers, reshaping the environment not through intention, but through chemistry. They also triggered a crisis for their microbial neighbors. For most of the life that had evolved in an oxygen-free world, oxygen was toxic. It was a reactive, corrosive gas that damaged cells and disrupted their chemistry. As cyanobacteria flourished, oxygen became more common in the oceans, creating zones where anaerobic life without oxygen, could no longer survive. Entire communities of microbes were forced into retreat, either pushed into oxygen-free pockets of the deep ocean or driven to extinction. It was one of the first ecological revolutions on Earth, and it came not from predators or disasters, but from microbes altering the atmosphere. And yet for other forms of life, oxygen opened new possibilities. It allowed for more efficient ways of extracting energy from food. This would eventually make larger, more complex life possible. In the deep arc of time, the cyanobacteria were laying the foundation for animals, plants, and us. But for now, their work was slow. Millions upon millions of years passed as they built stromatolites, as they released oxygen, as they left their mark in banded iron rocks. To human eyes, their pace might seem glacial, but on the scale of planetary history, they were rewriting the rules. Imagine floating above an ancient reef of stromatolites. The sea is shallow, clear in patches, murky in others. Here and there, bubbles rise as gases escape from microbial mats. Sunlight glitters off the surface, feeding colonies of cyanobacteria as they continue their silent labor. You are witnessing the quiet beginning of a transformation that will make Earth into the planet we know. Even today, cyanobacteria remain among the most successful organisms on Earth. They live in oceans, lakes, soils, and even deserts. They can survive in hot springs, in icy environments, and in waters rich with salt. Their resilience is unmatched. They are not only ancient pioneers, they are eternal survivors. As we reflect on them, we see a lesson in patience. The cyanobacteria did not reshape the planet overnight. They did it slowly, molecule by molecule, bubble by bubble, year after year, over vast stretches of time. Their story reminds us that even the smallest of actors can leave the largest of legacies. And so, in these shallow seas more than 2.5 billion years ago, the stage was set. The cyanobacteria had found their way to harness light and water, to release oxygen, and to multiply in abundance. They were not only thriving but transforming. In time, their oxygen would spill beyond the oceans, into the atmosphere itself, and the world would never be the same again. These were Earth's microscopic pioneers, unseen, unnoticed, yet unimaginably important. They were the breath before the breath, the quiet beginning of the Great Oxidation Event. Imagine drifting along the coastline of the ancient Earth, more than 2.5 billion years ago. The oceans spread wide and deep, greenish from dissolved iron, and the land is stark and barren. No trees, no grass, no plants at all. But if you wade into the shallow waters, you would find something extraordinary rising from the seafloor. Low, rounded mounds, stacked like pancakes or tiered like domes, pushing up from the sandy bottom. These are stromatolites, the ancient reefs built by microbial life. To modern eyes, they might look unremarkable, just lumps of stone, rounded and layered. But each stromatolite is alive, its surface coated with sticky mats of cyanobacteria. These microbes grow in thin films, trapping grains of sand and sediment as they photosynthesize. Layer by layer, they build up the mound, a living carpet of cells covering a mineral skeleton. Over decades, centuries, and millennia, stromatolites rise higher, forming structures that can be meters tall. In some shallow bays, they cluster together, creating entire landscapes of microbial reefs. They were, in many ways, the first great ecosystems of our planet. For billions of years, stromatolites were the dominant form of visible life on Earth. Long before forests, long before corals, even long before animals, these mounded reefs dotted shorelines across the globe. In their time, they were as common as coral reefs are today. The secret of their success lay in the cyanobacteria that built them. Each day, as the sun rose, the microbes absorbed its light, splitting water molecules and releasing oxygen. At night, the mats rested, but the sediment they had trapped remained. Over time, these layers created the striking banded structures that we still see in fossil stromatolites today. Some of these fossil stromatolites are more than 3.5 billion years old, among the oldest evidence of life on Earth. The appearance of stromatolites changed the landscape of the shallow seas. Wherever they grew, they stabilized sediments, altered currents, and created niches for other microbes. Tiny organisms could live within their layers, sheltered in the sticky biofilms. In this way, stromatolites became more than just structures. They were entire habitats, the first reefs built not of coral, but of bacteria, and yet, as they worked, the cyanobacteria were releasing oxygen into the waters. At first, that oxygen vanished into the chemistry of the seas, binding with iron to form rust, but the process never stopped. Every bubble, every layer, every mound of stromatolite was a testament to photosynthesis in action. The microbes had no idea that they were preparing the world for something entirely new. Imagine floating above a shallow bay of ancient stromatolites. The water is clear, sunlight dances across the rippled surface, and beneath you hundreds of mounds rise like domes. Their tops shimmer faintly with blue-green mats of life. Occasionally, small bubbles rise to the surface, the quiet exhalations of oxygen. The scene is serene, and yet it represents one of the most profound turning points in Earth's history. Stromatolites also left a gift to us, their fossils. Today, geologists can find them in rocks across the world. Some are found in Western Australia, others in South Africa, and even in parts of North America. When sliced open, the rocks reveal the distinctive, layered structures, rippling bands of sediment, captured and held by microbes billions of years ago. These fossils are not just stones, they are frozen moments of life, preserved across unimaginable time. Even more astonishing, stromatolites are not entirely gone. Though far rarer than in the past, they still exist in special environments where modern animals, like snails or worms, cannot graze them away. One of the most famous places to see them today is Shark Bay, in Western Australia. There, living stromatolites rise in shallow water, almost identical to those that flourished billions of years ago. To walk along that coastline is to walk through deep time, gazing at life's earliest monuments. The persistence of stromatolites reminds us of the resilience of cyanobacteria. Though their heyday has passed, their descendants continue to thrive in nearly every environment on Earth. From the hottest deserts to the coldest glaciers, from salty lakes to freshwater ponds, cyanobacteria survive and adapt. Their stromatolite structures may no longer dominate the seas, but their chemistry, photosynthesis, continues to power nearly all life on Earth. And yet, in their ancient abundance, stromatolites helped shape the future in more direct ways. By pumping oxygen into the oceans and skies, they triggered massive changes in climate and ecology. The methane, rich haze that once blanketed the skies began to thin. Sunlight reached the Earth's surface more strongly. The cooling effect that followed may have nudged the planet toward glaciations, perhaps even the first great snowball Earth episodes. For the anaerobic microbes that once ruled, the rise of stromatolites spelled trouble. Oxygen crept into their world, poisoning waters that had once been safe havens. Communities vanished, ecosystems collapsed, and the balance of life shifted. For many lineages of ancient microbes, the stromatolites' success was the beginning of the end. But for the planet as a whole, stromatolites were architects of a new age. Their reefs were not just habitats, they were engines of change, slowly preparing Earth for more complex life. In their layered stones, we see the quiet work of billions of years. We see persistence, patience, and transformation. So picture them again, the shallow seas dotted with microbial domes. Above, the sky glows faintly orange with methane haze. Below, oxygen bubbles drift upward, unnoticed by the world around them. The stromatolites continue their work, unaware of the revolution they are fueling. These reefs of bacteria, humble and unassuming, were among the first great shapers of Earth's history. Without them, without their endless layering, without their oxygen, the story of life would be different. Perhaps there would be no forests, no animals, no humans. Perhaps the planet would have remained a quiet, microbial world forever. The stromatolites remind us that greatness often begins in smallness. That even the simplest life, repeated over vast spans of time, can change the destiny of a planet. They were Earth's first builders, its first breath givers, and its first ecosystem engineers. In the calm of their shallow seas, they laid the foundations for everything to come. Close your eyes and imagine the ancient sunlight falling across the seas of early Earth. Each ray travels for millions of kilometers, through space, past planets and dust, before finally striking the ocean's surface. And there, Waiting just below the waves, tiny cells of cyanobacteria capture it. With pigments tuned to absorb light, they turn photons into energy, a process so elegant, so transformative, that it would forever reshape the destiny of our planet. This process is photosynthesis. Today, we take it for granted. Every breath we draw, every green leaf we see, every forest and meadow and plankton bloom depends on it. But billions of years ago, photosynthesis was an audacious experiment, discovered by microbes so small we could never see them without magnification. The principle is deceptively simple. Light is used to split water molecules apart. In doing so, electrons are harvested, energy is captured, and oxygen is released. But in that simplicity lies profound power. For the first time, life had found a way to use the most abundant resource on Earth, sunlight, and to draw upon the planet's endless supply of water. With those two ingredients, photosynthesis opened the door to limitless growth. At first, it was just one strategy among many. Other microbes had their own chemistries feeding on sulfur, iron, or methane. But photosynthesis offered something extraordinary. It tapped into a universal energy source, one that rose every day and bathed the planet in light. No volcano, no deep sea vent, no fleeting chemical niche could compete with the steady gift of the sun. The byproduct, of course, was oxygen. And oxygen, in that world, was dangerous for early life. It was a poison, reactive, corrosive, and disruptive to the fragile molecules that made up living cells. Yet for the cyanobacteria, oxygen was simply waste. They expelled it into the waters, bubble by bubble, unaware of the consequences. At first, those bubbles vanished almost as soon as they formed. Oxygen reacted with the dissolved iron in the oceans, rusting it into iron oxides that sank to the seafloor. The result was banded iron formations, layered rocks still visible today, stripes of red and gray, each band recording the breath of ancient photosynthesis. These rocks are not just stones. They are pages in Earth's diary, a record of life's planetary experiment. Over millions of years, the oxygen continued to flow. It filled shallow seas, then deeper waters. Still, it was captured and hidden, bound into rocks, minerals, and sediments. But photosynthesis did not stop. The experiment continued day after day, generation after generation, as microbes multiplied across the globe. The more they grew, the more oxygen they produced. It was like water dripping into a vessel, slow at first, then steady, then overwhelming. Eventually, the sinks that had hidden oxygen, the iron, the volcanic gases, the chemical sponges of the earth, began to fill. And as they filled, oxygen could no longer be contained. It began to linger in the atmosphere. It began to accumulate in the very air above the seas. Imagine that moment, the first molecules of oxygen rising from the ocean into the sky. Invisible, yet potent, they mingled with methane, oxidizing it into carbon dioxide and water. The delicate balance of the atmosphere began to shift. The haze that had shrouded the earth for so long thinned and disappeared. The skies cleared. The sun shone brighter on the surface, and the climate cooled, setting the stage for dramatic transformations to come. All of this because of photosynthesis, a planetary experiment run by microbes that never knew the scale of their impact. Their survival strategy had become a planetary force. Their quiet chemistry was rewriting the story of Earth. But this experiment was not without consequences. For the anaerobic microbes that had thrived in an oxygen-free world, photosynthesis was a catastrophe. As oxygen accumulated and the sea's habitats shrank, communities vanished. For some, survival meant retreating to oxygen-free environments, like the deep ocean or underground. For others, extinction was unavoidable. The oxygen revolution was in many ways the first great mass extinction in Earth's history, and yet oxygen also opened new doors. For those organisms that could tolerate or even use it, a new energy pathway emerged. Oxygen allowed life to extract far more energy from food. This efficiency would eventually make possible the evolution of complex cells, multicellular organisms, and much later animals. In this sense, photosynthesis was not just an experiment in survival, it was the foundation of possibility. The scale of time here is almost impossible for us to grasp. This was not a sudden event, but a slow unfolding across hundreds of millions of years. Generations of cyanobacteria lived and died, each one adding its infinitesimal contribution to the experiment. Together, they transformed the world. But for them, nothing changed. They were simply living, simply dividing, simply surviving. Today, we see photosynthesis as the most important biochemical process on Earth. It feeds the biosphere. It fuels the food chain. It fills the atmosphere with the oxygen we breathe. But when it first appeared, it was simply one of nature's many experiments. A quiet trial with results that no one, no microbe, no planet could have predicted. And so, as the ancient sun rose over microbial seas, photosynthesis continued its patient work. It was not a revolution in a single moment, but a tide that built slowly, relentlessly, reshaping oceans, skies, and life itself. From the smallest of cells came the largest of consequences. From the simplest of experiments came the greatest transformation in Earth's history. Photosynthesis was not just life adapting to the world. It was life beginning to create the world. A world that would soon enter a new age, the age of oxygen. Picture Earth's shallow seas more than 2.4 billion years ago. The water is warm green with dissolved iron and alive with mats of cyanobacteria. Each day, as sunlight filters through the waves, these microbes carry out their quiet labor of photosynthesis. They take in light and water, build sugars, and release oxygen as waste. At first, that oxygen has no chance to accumulate. It reacts instantly with iron, with volcanic gases, with minerals in the ocean. But slowly, very slowly, the balance begins to shift. Imagine standing on the shoreline of that ancient world. The air above you is still hostile, filled with methane, carbon dioxide, and nitrogen. But if you could kneel down and look closely at a mat of cyanobacteria, you might notice something remarkable. Tiny bubbles cling to the surface. Little spheres of oxygen, glimmering in the sunlight. They are fragile, bursting as soon as they rise, but their presence is a quiet hint of change. Geologists have found evidence of this oxygen leak in the rocks themselves. Some of the oldest signs come from minerals that only form in the presence of oxygen. Tiny pockets of sandstone, rippled and layered, contain structures where bubbles of gas were once trapped. The gas, preserved as voids in stone, tells us that oxygen had begun to seep into the shallow environments of early Earth. It was not yet abundant, but it was there, whispering of a new atmosphere to come. These first bubbles mattered because they marked a tipping point. For millions of years, oxygen had been bound away, absorbed by iron and sulfur in the seas. But as the sinks began to fill, some oxygen was free to rise into the air. At first it was patchy, appearing in small oases, shallow lagoons, sunlit bays, microbial reefs. In these places, oxygen levels spiked during the day, only to vanish at night when photosynthesis paused. Life experienced oxygen in pulses, moments of abundance, followed by its disappearance. This rhythm shaped evolution. Microbes that could tolerate oxygen survived the spikes. Those that could not retreated into deeper waters, clinging to places where oxygen never penetrated. It was an ecological shuffle, a sorting of winners and losers in the new chemical world. The bubbles also began to affect the larger atmosphere. As oxygen crept into the skies, it started to interact with methane. Methane, once the dominant greenhouse gas, was vulnerable to oxidation. Oxygen stripped it away, turning it into carbon dioxide and water vapor. And though carbon dioxide is still a greenhouse gas, it is far less potent than methane. As methane levels fell, Earth began to cool. The evidence of this cooling is etched into ancient rocks. Glacial deposits from around 2.4 billion years ago hint at widespread ice, perhaps even the first snowball Earth events. Imagine the planet, once warm and hazy, now slipping into cold. The skies clear as the methane haze dissolves. The sun's rays strike more directly, and ice begins to spread across the continents, reflecting more light, deepening the chill. All of this tied back to those first oxygen bubbles, rising from microbial mats in the shallows. But for the microbes themselves, nothing seemed so dramatic. They continued their work, building stromatolites, releasing oxygen, shaping sediments. The bubbles they produced were small, fragile, fleeting, and yet they were reshaping the chemistry of the entire world. It is humbling to think of how such small processes can change so much. The bubbles we see preserved in ancient rocks are like signatures, proof of life's power. Each one tells a story. Here, in this place, microbes captured sunlight, split water, and exhaled oxygen. Here the world took one more step toward transformation. Some scientists believe these oases of oxygen may have been refuges for early eukaryotes. the more complex cells that would eventually give rise to animals and plants. Though eukaryotes would not fully flourish until later, these first flickers of oxygen may have created the conditions they needed to evolve. In this way, the oxygen leak was not just a chemical curiosity. It was a doorway, opening the path for the rise of complexity. Picture again those shallow seas. The mats of cyanobacteria glisten in the light. Tiny streams of bubbles drift upward, breaking the surface in silence. To us, they are symbols of life's creativity, but to the microbes, they are just waste. And yet, this waste would soon change everything: the air we breathe, the climate we live in, the very possibilities of life itself. The oxygen leak was the planet's first breath, a hesitant, fragile exhalation, but once released, there was no turning back. The world was beginning to inhale oxygen, and with it, to enter a new age. If you have ever walked through a desert, or seen the deep red cliffs of places like Arizona, you've witnessed the legacy of oxygen in stone. Those striking colors, the rusty reds, the earthy browns, come from iron that has reacted with oxygen, and billions of years ago. Long before deserts and canyons, the Earth's first red beds began to form. They are not just rocks. They are pages in the planet's diary recording the earliest breaths of oxygen. To understand them, we must go back to the oceans of early Earth. For millions of years, oxygen produced by cyanobacteria was trapped in the seas, where it reacted with dissolved iron. The oceans, rich with iron washed from volcanic rocks, acted as a sponge, soaking up oxygen as fast as it was made. The result was a rain of rust, iron oxides that settled on the sea floor in alternating bands with other sediments. These became the famous banded iron formation stripes of gray and red, recording the slow saturation of the oceans. But as time went on, the iron sponge began to fill. The oceans, once able to hide oxygen in their depths, could no longer absorb it all, and so oxygen began to spill into the air. For the first time, it lingered in the atmosphere long enough to change the chemistry of the land. This is where the red beds appear. When rocks rich in iron were exposed to the air, the oxygen in the atmosphere reacted with them. Instead of staying gray or black, the sediments turned reddish. Grains of sand coated in iron rusted just as metal rusts today. The result was entire layers of sandstone stained in hues of red, orange, and brown. To geologists, these rocks are a revelation. They tell us that by around 2.4 billion years ago, oxygen had reached a level in the air sufficient to oxidize iron on land. It was no longer just an oceanic phenomenon. The planet itself had changed. The Earth had begun to breathe oxygen. Imagine walking across an ancient floodplain at that time. Rivers wind lazily across the landscape, carrying iron-rich sediments from eroding volcanic rocks. As the sediments are laid down, the oxygen in the atmosphere seeps into them, turning them reddish. Layer by layer, season by season, the diary of oxygen is written in stone. These red beds are still visible today. Across South Africa, Canada, and India, geologists find them in rocks dating back to the Great Oxidation Event. Each outcrop is a window into the past, a reminder that the air above us has not always been the same. What we take for granted, a sky filled with oxygen, was once an innovation recorded in iron and stone. The beauty of red beds lies in their simplicity. They are not complex fossils or rare minerals. They are ordinary sandstones and siltstones, stained by rust. And yet, in their colors we see the first true evidence that oxygen was no longer confined to the seas. It was shaping the land, altering the chemistry of soils, rivers, and deserts. The arrival of oxygen in the atmosphere was not a gentle change. It disrupted everything. Anaerobic microbes, which had thrived in oxygen-free conditions, now faced an environment that was turning toxic. Entire microbial ecosystems vanished from the surface and retreated underground or into deep anoxic basins in the ocean. At the same time, iron-rich minerals began to weather differently. Volcanoes erupted into an atmosphere that could transform their gases in new ways. The planet's chemistry had entered a new era. The red beds are the proof. They are the lines in the diary where Earth shifted from one chapter to the next. They show us the very moment when oxygen stopped being a local phenomenon and became a global presence. Think of the patience required for this change. It took hundreds of millions of years for oxygen to accumulate to levels where rocks could rust in the open air. Hundreds of millions of years of cyanobacteria, tirelessly releasing oxygen into their surroundings. Each cell, each colony, each stromatolite playing its part in the great experiment of photosynthesis. And finally, after so much time, the evidence appears in stone, a blush of red across ancient sediments. There is something poetic about this. The color of rust, so often a sign of decay, here becomes a symbol of creation. It marks not the end of something, but the beginning of a new world. A world where oxygen would allow new kinds of chemistry, new kinds of life, and eventually, complexity beyond imagination. Today, when we see red rocks in the desert, we are seeing echoes of that ancient shift. The same chemistry that stained the earth billions of years ago still colors the land around us. Every rusty hue is a reminder of the Great Oxidation Event and the microbes that made it possible. So picture it: the earth, once gray and hazy, now beginning to glow with red. Floodplains and deserts stained in iron oxide, under skies that carried the first meaningful traces of oxygen. It was a silent transformation, but one that would shape the destiny of life. The red beds are Earth's diary, written in the language of rust, and in their pages, we find the first clear signs that the planet had entered a new age, the age of oxygen. Take a slow breath in and out. The air feels effortless, filled with oxygen, invisible yet vital. It is hard to imagine a world without it, and harder still to imagine that oxygen once struggled for billions of years to take hold. But the rise of oxygen was not sudden. It was a long build-up, a slow climb against resistance, a struggle between life and the chemistry of the planet. We often think of cyanobacteria as triumphant pioneers, pumping oxygen into the air, and in time, that is what they did. But in the beginning, most of the oxygen they produced never lingered. It was captured, consumed, hidden away by the earth itself. One of the largest sinks for oxygen was the ocean. The seas of early Earth were rich in dissolved iron, washed down from volcanic rocks and hydrothermal vents. As soon as oxygen appeared, it reacted with the iron, forming rust that sank to the seafloor. Over millions of years, this process created vast deposits of banded iron formations. Layer after layer, the oceans quietly locked away oxygen in stone. Sulfur, too, played a role. Volcanoes released gases filled with sulfur compounds. When oxygen encountered them, chemical reactions stripped it away, binding it into sulfates. The planet was a vast chemistry lab, consuming oxygen faster than it could accumulate. Even the Earth's crust was a thief of oxygen. Fresh volcanic rocks, full of reactive minerals, soaked up oxygen as they weathered. Every raindrop that fell on a lava flow, every river that carved through basalt, provided surfaces for oxygen to vanish into. The land itself was hungry and oxygen was its meal. And so, for hundreds of millions of years, oxygen remained trapped in cycles, produced by cyanobacteria, consumed by rocks, iron, and gases. It was present in bursts, in shallow waters, in oases where microbes flourished. But it never lasted long enough to transform the air above the seas. This is why scientists sometimes describe the rise of oxygen as a great delay. Photosynthesis may have begun more than 3 billion years ago, but significant oxygen in the atmosphere did not appear until about 2.4 billion years ago. That gap of time, nearly 600 million years, was filled with struggle. Imagine it as a balanced scale. On one side, cyanobacteria endlessly producing oxygen. On the other, the Earth itself endlessly absorbing it. For eons, the balance tipped toward the planet. Oxygen was produced, but always captured. The atmosphere remained methane-rich, hazy, and alien. But slowly, imperceptibly, the sinks began to fill. The oceans could only hold so much iron. The volcanic gases slowed as Earth's interior cooled. The crust, already weathered in many places, became less reactive, and the balance began to tip. It was not a sudden moment, but a gradual shift. As the sinks filled, more oxygen escaped. Tiny amounts lingered in the atmosphere, enough to oxidize sediments on land, enough to create red beds. Still, it was not stable. Oxygen levels rose and fell like a tide. Periods of accumulation were followed by crashes, as geological or biological changes pulled oxygen back down again. This fluctuation may have lasted for millions of years. Earth's atmosphere seesawed between states, sometimes richer in oxygen, sometimes nearly devoid of it. For life, it was both a challenge and an opportunity. Anaerobic microbes clung to oxygen-free refuges, while others began to adapt, experimenting with ways to tolerate or even use oxygen. In these experiments, evolution found its next great path. Some organisms developed enzymes to neutralize oxygen's toxicity. Others found ways to use it in metabolism, unlocking far more energy than before. These adaptations were rare at first, but they planted the seeds for the future. Meanwhile, the planet itself was changing. As methane levels dropped, oxidized by oxygen into carbon dioxide and water, Earth began to cool. Ice spread, perhaps plunging the planet into its first global glaciations. Some scientists believe these snowball Earth events were triggered by the very rise of oxygen as the atmosphere shifted from methane, rich, to carbon dioxide dominated. It was a world in flux, caught between ancient stability and new chemistry. The long build-up teaches us a lesson about time. The forces that shaped our atmosphere did not work quickly. They unfolded slowly, over billions of years, with each generation of microbes contributing only a whisper of change. And yet, those whispers accumulated. Like drops of water filling a vessel, they eventually overflowed, and oxygen could no longer be contained. We can think of it like pressure behind a dam. For eons, the dam of iron, sulfur, and rocks held back the flood. But as it filled, cracks began to appear. At first, only trickles of oxygen escaped, then more. And finally, the dam gave way, and oxygen surged into the atmosphere, transforming the world. When we inhale today, we are breathing the result of that long build-up. Our atmosphere is the inheritance of cyanobacteria, of banded iron formations, of volcanic gases, of red beds. It is a story of patience and persistence, of slow accumulation against resistance. The Great Oxidation Event was not a single moment, but the culmination of this long struggle. It was the tipping point, after hundreds of millions of years of balance and delay. And in that tipping point, life in Earth entered a new chapter. So imagine again that early world. The seas rust red with iron deposits, the air hazy with methane, tinged orange under a faint sun. And yet, just beneath the surface, oxygen bubbles rise from microbial mats. Most vanish into the chemistry of the ocean, but a few escape, drifting upward into the sky. They are fragile, fleeting, but together, over time, they gather into something enduring. That was the long build-up, a patient, invisible preparation for a revolution to come. Take a slow breath and picture Earth more than 2.4 billion years ago. The skies are beginning to change. For billions of years, they had been heavy with methane, a gas exhaled by ancient microbes, trapping warmth beneath a faint young sun. That methane had kept the oceans liquid, the winds flowing, the planet alive. But with oxygen now rising, that balance was about to collapse. Methane is a greenhouse gas, and a powerful one, even in small amounts. It holds heat far more effectively than carbon dioxide. For much of Earth's early history, methane was the guardian of warmth, compensating for a sun that glowed only 70% as brightly as it does today. Without methane's blanket, the Earth would have frozen. With it, the seas stayed liquid, and life flourished in its microscopic ways. But oxygen and methane are uneasy partners. When oxygen entered the atmosphere, it reacted with methane, stripping it away. The chemical reaction turned methane into carbon dioxide and water vapor. And while carbon dioxide can still trap heat, it is a weaker greenhouse gas. The atmosphere, once rich and protective, thinned in its ability to hold warmth. The consequences were dramatic. As methane collapsed, Earth's climate began to cool. The hazy orange skies cleared, the blanket of warmth dissolved, and sunlight struck the surface more directly. At first, this may have seemed like a subtle shift, a few degrees colder, a longer winter. But over thousands and then millions of years, the cooling deepened. Ice spread from the poles, glaciers advanced, and perhaps for the first time, Earth descended into a state of near global freeze. This may have been the first of Earth's great snowball Earth episodes, times when ice reached the equator, covering nearly the entire planet in white. Imagine the oceans sealed beneath kilometers of ice, continents locked in frozen silence, and sunlight reflected back into space by a planet gleaming in frost. For life, this was a profound challenge. Anaerobic microbes, already pushed into hiding by oxygen, now faced cold and scarcity. Communities clung to refuges, cracks in the ice, volcanic hot springs, deep-sea hydrothermal vents where warmth still pulsed from the Earth's interior. It was not extinction, but survival on the edge. Life endured as it always had, finding niches even in the harshest of climates. But the balance of power had shifted. The methane world was gone. In its place, an oxygen and carbon dioxide atmosphere ruled, with colder temperatures and clearer skies. Geological evidence tells us of this cooling. Ancient rocks preserve signs of glaciation. Scratched surfaces where ice dragged stones, deposits of glacial till left behind as the ice melted. These marks appear in layers dating back to around the time of the Great Oxidation Event, suggesting that oxygen's rise and methane's fall were tied directly to a planetary freeze. The collapse of methane also changed the chemistry of the air. The thick haze that had once blanketed Earth disappeared. For billions of years, that haze had filtered sunlight, scattering it into an orange glow. With the haze gone, the skies turned blue for the first time. The sun shone brighter, the stars sharper, the day clearer than ever before. It was as if the planet had wiped its eyes and awakened to a new light. The cooling also reshaped the oceans. Ice capped their surfaces, but beneath, the chemistry shifted. With less methane bubbling up from microbial mats and more oxygen filtering downward, the balance of nutrients and gases changed. The oceans were no longer the same rich, iron-dominated seas. They were becoming more oxidized, more layered, more complex. The groundwork for future ecosystems was being laid in the cold, dim waters beneath the ice. For the planet, this transition was not a disaster but a transformation. The collapse of methane forced Earth into a new climate regime, one more suited to stability over the long term. Methane is unstable in the presence of oxygen. It cannot coexist in abundance. But carbon dioxide and oxygen together create a more balanced, self-regulating atmosphere. This new balance would prove more enduring, supporting the slow rise of complexity that lay ahead. It is tempting to see this cooling as harsh, even hostile. But in deep time, it was a cleansing. The methane blanket had served its purpose, protecting life when the sun was faint. Now, as the planet matured, oxygen prepared it for a different destiny. The frozen interludes may have been severe, but they also may have spurred innovation, pushing life to adapt, to survive, and eventually to thrive in new ways. Imagine yourself standing on one of those frozen shorelines. The land is silent, barren, covered in ice. The seas are sealed, though beneath them microbial life persists. The air is cold, sharp, clearer than it has ever been. Above, the stars blaze in the dark sky, unmarred by haze. The planet looks still, almost asleep. And yet, in its stillness, it is becoming something new. This was the price of oxygen. The loss of methane, the fall of warmth, the spread of ice. But it was also the promise of oxygen, clearer skies, new chemistry, new opportunities for life. The collapse of methane was not an ending. It was the opening of the next chapter. And so, as Earth cooled beneath its new sky, the stage was set. Life had survived oxygen. It would now survive the cold. And in the struggle, it would prepare itself for even greater transformations to come. Imagine looking at Earth from space, 2.4 billion years ago. It does not shine as the blue and green marble we know today. Instead, it gleams white, a frozen orb wrapped in ice. Glaciers stretch across the continents, seas are capped with frozen crust, and even the equator lies beneath snow. This is the vision of Snowball Earth, a planet locked in deep freeze. Was the entire world truly frozen solid? Scientists still debate. Some argue that the ice reached from pole to pole, covering every ocean, every bay, every coastline. Others suggest a slushball Earth, where thick ice extended nearly to the equator, but left small patches of open water near the tropics. Whatever the exact extent, the evidence is clear. Earth endured profound glaciations during and after the Great Oxidation Event. The signs are carved into ancient rocks. In South Africa and Canada, layers of glacial deposits appear in strata dating back 2.4 billion years. Stones and boulders carried by glaciers were dropped into marine sediments as icebergs melted, leaving telltale marks called dropstones. Other rocks bear scratches, gouges made by ice dragging across bedrock. Together, they tell a story of ice advancing far beyond what had ever been seen before. The trigger for this deep freeze was oxygen itself. As oxygen accumulated in the air, it stripped away methane, Earth's strongest greenhouse gas. The blanket of warmth that had long protected the planet vanished, leaving only the weaker greenhouse effect of carbon dioxide. The faint young sun could not keep pace. The result was global cooling, the spread of glaciers, and a world transformed into ice. For life, The snowball Earth was a trial of endurance. Cyanobacteria, the very architects of the oxygen revolution, now faced a planet where sunlight was trapped beneath ice. Their photosynthetic activity slowed, limited to cracks, thin ice near the equator, or meltwater pools where light still penetrated. Anaerobic microbes already forced into hiding by oxygen now retreated further, clinging to hydrothermal vents and geothermal refuges. Life persisted, but it was pushed to its limits. And yet, even in this frozen world, opportunities emerged. The ice acted as a protective shell, stabilizing the oceans beneath it. In the dark waters below, microbial communities continued, sheltered from surface extremes. Volcanic activity released nutrients into the seas, supporting pockets of growth. And in places where ice thinned or fractured, cyanobacteria continued their photosynthetic labor, adding still more oxygen to the air. The snowball Earth, paradoxically, may have accelerated the oxygenation process. As methane collapsed and ice spread, cyanobacteria still survived, still exhaled oxygen, and still changed the planet. When the ice finally receded, the world emerged into an atmosphere more oxygen-rich than before. The crisis had become a catalyst. We might imagine the planet during these icy ages as silent, still, and lifeless. But silence can be deceptive. Beneath the ice, chemistry continued. Life adapted. Evolution never stopped. The seeds of complexity were being sown in the dark oceans, waiting for the right conditions to bloom. The glaciers themselves became part of the story. As they ground across continents, they scraped and eroded rocks, releasing minerals and nutrients. When the ice melted, these nutrients washed into the oceans, fueling microbial blooms. The frozen years may have seemed harsh, but they prepared the seas for bursts of growth that followed. There is also beauty in the vision of a snowball Earth. Picture it from orbit, a brilliant white sphere, gleaming against the black of space, clouds swirling over endless fields of ice. The sun's rays reflect sharply, the planet brighter than ever before. It looks fragile, delicate, asleep. And yet, within that frozen shell, life holds on. It waits, patient, enduring, shaping the future even in hardship. The question remains, was it truly global, or only near global? Did the equator remain ice-free, a thin ribbon of open water beneath the sun's weak glow? Did cyanobacteria gather there, concentrated in refuges, working harder than ever to release oxygen into the skies? Or was the ice unbroken, forcing life to survive only in cracks, vents, and hidden places? The rocks preserve clues, but not certainty. And perhaps that mystery is part of the story, a reminder that even with billions of years of evidence, Earth still keeps some secrets. What we know is this: oxygen transformed the atmosphere, methane collapsed, and Earth cooled. The result was glaciation on a scale never seen before. Whether the planet was a full snowball or a slush ball, it was a world under ice. And when the ice retreated, the Earth that emerged was forever changed. The snowball Earths of the Great Oxidation Event were not the last. They would return in later ages, echoing through the Proterozoic, testing life again and again. But this first great freeze was the beginning, the moment when oxygen's power was felt not just in rocks or shallow seas, but across the entire climate system. Imagine standing at the edge of one of those ancient glaciers. The air is thin, cold, and sharp. The horizon is nothing but ice, stretching endlessly. Beneath your feet, the planet sleeps, wrapped in a frozen blanket. But deep below, in dark oceans and steaming vents, life continues. And above, cyanobacteria, in cracks, in melt pools, in sunlit shallows, continue their patient work, exhaling oxygen, step by step, reshaping the future. This was Earth's trial by ice, a frozen chapter in the long story of oxygen. And though the world looked still, it was not the end. It was only a pause, a deep breath. Before life's next great transformation, breathe in deeply. The air feels cool, nourishing, and effortless. But for much of life on the early Earth, oxygen was not a gift. It was a toxin, a silent, invisible threat that destabilized the world they had known for billions of years. To us, oxygen is essential. It fuels our cells, allows us to walk, to think, to dream. But oxygen is also reactive, a molecule eager to bond, to break, to burn. It corrodes metals, feeds flames, and damages delicate biological structures. To the microbes that first evolved in a world without it, oxygen was a danger to be avoided. For billions of years before the Great Oxidation Event, life thrived without oxygen, Anaerobic microbes dominated the seas, living off sulfur, methane, and iron. Their metabolisms were perfectly tuned to an oxygen-free world. For them, oxygen was not simply useless. It was disruptive, even deadly. When cyanobacteria began releasing oxygen through photosynthesis, at first, oxygen vanished quickly, bound up in rocks, minerals, and dissolved iron. But as the sinks filled, oxygen began to accumulate. It crept into shallow seas, then into deeper waters, and eventually into the air itself. The very atmosphere of the planet was changing, and with it, the fates of countless organisms. Imagine being one of those ancient anaerobic microbes. For generations, your ancestors thrived in chemical stability. Now, suddenly, your world is poisoned. Oxygen seeps into your environment, breaking apart your cellular machinery, interfering with your chemistry. Survival becomes difficult. Some microbes retreat to the deep ocean, where oxygen cannot reach. Others hide in sediments buried in anoxic mud, but many cannot escape. They die in waves, extinguished by a molecule we now depend upon. This was the first great ecological crisis in Earth's history. A mass extinction, not caused by asteroids or volcanoes, but by life itself. Microbes poison their own world, not through malice or intent, but by following their own path of survival. The byproduct of photosynthesis, oxygen, became the downfall of those unable to adapt. The crisis was global, and yet it was uneven. Some parts of the oceans became oxygen oases, where cyanobacteria flourished and oxygen pooled during daylight. In these places, anaerobes vanished. Elsewhere, deep basins and stagnant waters remained oxygen-free, serving as refuges. The biosphere split into two realms: oxygen, rich habitats, and oxygen, poor havens. It was a world divided. With winners and losers separated by a molecule, the survivors found ways to cope. Some evolved enzymes that neutralized oxygen's reactive power: catalases, peroxidases, and superoxide dismutases, tiny molecular shields that broke down dangerous oxygen byproducts. Others went further, learning to use oxygen itself as fuel. By harnessing oxygen in respiration, these microbes unlocked more energy from food than ever before. Though rare at first, they were the ancestors of everything to come. But in this moment, during the Great Oxidation Event, the overall story was one of loss. Anaerobic diversity declined. Whole ecosystems disappeared. The balance of Earth's biosphere shifted forever. The rocks preserve evidence of this crisis. In sediments from this time, we see sudden changes in isotopes of sulfur, markers of a shift in atmospheric chemistry. We see layers of iron oxides, recording oxygen's relentless rise. And we see gaps in the fossil record of microbial mats, signs of collapse and change in once thriving communities. The story feels harsh, but it also feels familiar. Oxygen was not the last disruptor. Throughout Earth's history, life has transformed the planet, often in ways that make it hostile for earlier forms. The rise of plants would later reshape carbon dioxide levels. The rise of animals would alter food webs. Each revolution brought new opportunities, but also new extinctions. The Great Oxidation Event was the first, and perhaps the most profound. It is worth pausing here to imagine the emotional shape of this story. To us, oxygen is life. To them, oxygen was death. The very molecule that makes our existence possible once swept through the biosphere like a silent plague. And yet, it was not deliberate. The cyanobacteria were not conquerors. They were simply living, photosynthesizing, multiplying. The crisis was an unintended consequence, a reminder of how interconnected the web of life truly is. Still, from this crisis came possibility. By wiping out much of the anaerobic world, oxygen cleared space for new forms of life. It forced innovation, driving evolution toward complexity. Without this purge, multicellular life might never have emerged. Without this crisis, we might not exist. So imagine again the ancient seas divided between oxygen and anoxia. In the shallows, cyanobacteria thrive, their mats bubbling with oxygen. In the depths, survivors huddle, clinging to environments untouched by the new gas. Between them lies a battlefield invisible to the eye, where chemistry decides survival. It was the first great ecological crisis, a crisis of breath, of balance, and of life against life. And though it was devastating, it was also transformative. Because in oxygen's poison lay the seeds of a future where oxygen would mean power. Take another slow breath in and out. For us, oxygen is comfort. But for the life that first inhabited our planet, oxygen was catastrophe. It was a creeping poison, turning once habitable oceans into deadly traps, and for billions of years of Earth's history, those earlier, oxygen-free worlds were all that life had known. When oxygen began to rise during the Great Oxidation Event, it set in motion one of the first great mass extinctions in Earth's history. It was not sudden, not explosive, not a single disaster that swept across the globe. Instead, it was slow, insidious, and relentless. A silent extinction carried out molecule by molecule. Anaerobic microbes had thrived since the dawn of life. They lived by breaking down methane, sulfur, and iron. They built vast mats across shallow seas, filled hydrothermal vents with activity, and spread across continents in invisible films. For billions of years, they were the rulers of Earth. But when oxygen entered the picture, their dominance was challenged. At first, they could retreat. When oxygen oases appeared in shallow waters, anaerobes slipped into deeper basins. When surface sediments became toxic, they buried themselves in mud. But as oxygen spread, these safe havens grew smaller. The very seas that had nourished them were turning hostile. The biochemistry of their cells could not withstand oxygen's reactivity. Proteins unraveled. Membranes oxidized. Molecules essential for survival were broken apart. Whole populations dwindled, collapsing not because of predators, but because the air and water themselves had changed. This extinction was not visible in grand skeletons or dramatic fossil beds. It was microbial, microscopic, written in the subtle layers of stone. Geologists read it in the sudden decline of sulfur isotope variations, in the disappearance of certain microbial mats, in the global chemical signals locked into rock. The clues whisper of a biosphere under stress, of ecosystems vanishing in silence. For the microbes that survived, adaptation was the only path. Some evolved defenses, enzymes to break down toxic oxygen byproducts. Others went further, transforming oxygen from poison into power. By harnessing oxygen in respiration, they unlocked far more energy than ever before. This innovation would eventually lead to the evolution of eukaryotes, and later, multicellular life. But in this moment, during the Great Oxidation Event, the story was one of loss. The scale of extinction is difficult to comprehend. Entire lineages disappeared, leaving no descendants. The microbial diversity of the early Earth, once vast and varied, narrowed dramatically. What survived was only a fraction of what once existed. Life had been reshaped, pruned by oxygen's rise. Imagine again the shallow seas of 2.4 billion years ago. At the surface, stromatolites bubble with oxygen, their cyanobacterial mats thriving in the sunlight. But below, where anaerobic microbes once blanketed the seafloor, silence spreads. Communities wither, leaving behind only traces in sediment. The water grows clearer, less turbid with microbial haze. The oxygen keeps coming, indifferent to the destruction it causes. It was not a swift collapse, but a drawn-out process. For millions of years, oxygen crept outward, expanding its reach, squeezing anaerobes into tighter and tighter corners of the biosphere. Some survived in deep oceans where oxygen could not penetrate. Others found refuge underground in pores of rock or deep sediments. Even today, descendants of those survivors persist in oxygen-free environments, in mudflats, in salt marshes, in hydrothermal vents. They are reminders of the world before oxygen, fossils made of flesh and chemistry. But their diversity is nothing compared to what once was. The Great Oxidation Event cut deeply, reducing the microbial kingdoms of Earth in ways we can only glimpse. It was one of the earliest, and one of the most consequential, mass extinctions in history. And yet from that loss, opportunity emerged. By clearing the stage of anaerobic dominance, oxygen opened the door for new ecosystems. Life that could tolerate oxygen, or even exploit it, found room to grow, expand, and diversify. The collapse of one world made way for the rise of another. It is a reminder of the dual nature of extinction. It is tragedy for those who vanish, but also chance for those who remain. In the story of life, endings and beginnings are often bound together. So picture again that ancient planet, caught in transition. The orange haze of methane has cleared, replaced by blue skies brightened by oxygen. The seas shimmer under glaciers, their chemistry shifting with every bubble of oxygen. Anaerobic life retreats, reduced, diminished, but elsewhere new possibilities stir. Cells are learning to breathe oxygen, to turn poison into energy, to pave the way toward complexity. The Great Oxidation Event was a cataclysm, yes, But it was also the first great reshaping of life's tree. It pruned ruthlessly, but it also prepared the ground for branches that would grow taller, broader, and more intricate than ever before. The mass extinction of anaerobic life was not the end of the story. It was the painful beginning of a new one, a world where oxygen was no longer an intruder, but the atmosphere itself. Take a calm breath in and let it go. For us, oxygen feels like life itself, flowing effortlessly through our lungs. But on the early Earth, oxygen was new, dangerous, and untested. Life had to learn how to live with it. And in doing so, some microbes discovered not just survival, but power. When anaerobic life collapsed under the toxic spread of oxygen, only the adaptable survived. Among them were lineages of microbes that began to experiment with using oxygen, not avoiding it. This was the birth of aerobic life. Organisms that could breathe oxygen, turning it from a threat into a tool. Why was this so important? Because oxygen offered a gift unlike anything life had known before: energy. Anaerobic respiration, using sulfur, iron, or methane, provided only a little energy per molecule of food. Enough to survive, enough to multiply, but never enough to build complexity. Oxygen changed that. With aerobic respiration, cells could extract far more energy from the same amount of food. It was like exchanging a candle for a blazing fire. This energy surplus gave aerobic life an advantage. They could grow faster, adapt quicker, and survive in more varied environments. They could power more intricate cellular machinery, laying the groundwork for complexity yet to come. At first, though, they were few. The rise of oxygen had been uneven, with some parts of the oceans rich in it and others still starved. Aerobic microbes found niches in oxygenated shallows, clinging to the new environments cyanobacteria had created. Anaerobes still thrived in deeper, darker waters far from oxygen's reach. The biosphere was patchy, divided between two worlds. Geological evidence tells us of this slow rise. In certain rocks, we see traces of microbial activity tied to oxygen use. In chemical signals, we find evidence that oxygen was not everywhere, but appearing in bursts, oozes, and expansions. It was not a sudden takeover. It was a gradual, uneven spread. The Earth itself played a role in this pacing. Volcanoes continued to release gases that consumed oxygen, slowing its accumulation. The oceans still absorbed oxygen into their depths, reacting with sediments and minerals. It was as though the planet resisted, absorbing as much as it could, only slowly yielding to the presence of oxygen. And so, aerobic life did not explode into dominance. It crept forward, colony by colony, tide pool by tide pool. It was patient, steady, persistent. The world was not yet ready for its full potential, but the seeds had been planted. Imagine one of those shallow seas. By day, mats of cyanobacteria bubble oxygen into the water. Nearby, aerobic microbes gather, using that oxygen to breathe, to extract energy to grow. They are invisible to the naked eye, but in their chemistry, they are pioneering the path that will one day lead to animals, forests, and humans. This rise was not without struggle. Even as they used oxygen, aerobic cells had to protect themselves from its dangers. Reactive oxygen molecules could still damage DNA, proteins, and membranes. Microbes developed antioxidants and enzymes, small shields against oxygen's double-edged nature. These defenses became permanent features of aerobic life, passed down even to us. When our cells use oxygen today, they still rely on these ancient protections. It is humbling to think of how much of our biology was shaped in this distant age. Our mitochondria, the powerhouses of our cells, are descendants of ancient aerobic bacteria. They carry within them the legacy of this slow rise, the memory of a time when oxygen was a novelty and an opportunity. But in this chapter of Earth's story, aerobic life was still young. It had not yet risen to grandeur. It remained small, microbial, fragile. The oxygen levels in the atmosphere were still low compared to today, perhaps only a few percent. Enough to support microbes, but not enough yet for large, complex creatures. The slow rise of aerobic life reminds us that revolutions in nature are rarely instant. The Great Oxidation Event was a turning point, but its effects unfolded over eons. Life adapted step by step, generation by generation, until oxygen became not just tolerable, but indispensable. Picture again that ancient shoreline. The skies are clearer now, bluer than they once were. The seas ripple with light, no longer green with dissolved iron, but slowly shifting toward new chemistries. And in those waters, aerobic microbes breathe deeply, quietly shaping the future. Their success is not loud. There are no sudden bursts of animals, no forests rising overnight. Only tiny cells multiplying, exchanging genes, perfecting the art of using oxygen. But within them lies the promise of complexity, a promise that will take more than 1 billion years to fulfill. The mass extinction of anaerobes had cleared space, and aerobic life stepped into it slowly, cautiously but surely. It was not the end of life's struggles with oxygen. There would be more crises, more extinctions, more snowball Earths. But the path had been set. The Earth was no longer a world of methane and haze. It was a planet of blue skies, oxygen oases, and aerobic pioneers. A planet reshaped by chemistry and by the smallest of creatures with the simplest of strategies. And from these beginnings, all future complexity would grow. Close your eyes and drift downward into the oceans of the Great Oxidation Event. The surface glitters with sunlight, cyanobacteria float in mats just below, and bubbles of oxygen rise quietly toward the sky. But beneath the waves, deeper and darker, the oceans are not yet the blue we know today. They are chemical seas, green with dissolved iron, tinged with sulfur, layered in ways that reveal the slow transformation of the planet. The oceans of early Earth were rich in iron, because volcanic activity and erosion continually delivered it to the waters. In the absence of oxygen, this iron remained dissolved, giving the seas a metallic, almost blood-red chemistry. But as cyanobacteria released oxygen, the balance began to shift. Oxygen reacted with iron, rusting it into insoluble oxides that sank to the seafloor. Over time, vast layers of banded iron formations were built, stripes of red and gray, that still cut through ancient rocks today. These formations are silent testimony to the chemical dialogue between microbes and the oceans. The chemistry of the oceans during this time was dynamic, shifting between oxygen-rich and oxygen-poor states. In shallow, sunlit waters, oxygen levels sometimes rose high enough to support aerobic life. But deeper down, the oceans often remained anoxic, starved of oxygen, and still rich in iron and sulfur. This created a layered world with different chemistries stacked upon one another like invisible blankets. At the surface, oxygen oases flourished. Below, anaerobic microbes held on, feeding on methane, sulfur, and iron. Between them lay a zone of chemical gradients, shifting boundaries where oxygen and reduced compounds met, sparking reactions that fueled entire ecosystems of microbes. These boundaries were alive with possibility. Sulfur was especially important. Volcanoes belched sulfur gases into the air, which dissolved in the oceans. In the absence of oxygen, sulfur circulated in reduced forms, available to anaerobic microbes as food. But when oxygen entered the picture, sulfur was oxidized into sulfates. This changed not only the chemistry of the seas, but also the cycles of nutrients that life depended on. These shifts were not instantaneous. They took millions of years, even hundreds of millions, to play out. The oceans resisted oxygenation just as the atmosphere had. Iron, sulfur, and organic matter absorbed oxygen as quickly as it appeared. The seas were sinks, pulling oxygen down into their depths, slowing its spread. It was as though the oceans were reluctant to change, clinging to their ancient chemistry, and yet change came. As oxygen levels built, the iron sponge of the seas grew saturated. Less and less dissolved iron was available. The oceans began to clear, losing their greenish haze. Nutrients cycled differently, reshaping ecosystems. New microbial strategies emerged, with some life thriving on oxygen, others on the oxidized compounds it created. Geologists today trace these changes in the rocks. They find shifts in sulfur isotopes, marking the rise of oxygen and the decline of the sulfur cycle. They find banded iron formations giving way to red beds, signaling the movement of oxygen from the oceans into the air. They find chemical fingerprints in sediments, recording the first stirrings of an oxidized world. It is easy to forget how profoundly these chemical changes mattered. Oceans are not just water. They are the lifeblood of the planet, circulating nutrients, regulating climate, and sustaining life. As oxygen seeped in, it altered everything: how carbon was buried, how minerals formed, how energy flowed through ecosystems. It was as though the very bloodstream of Earth was rewired. For life, this was both a challenge and an opportunity. Anaerobes that had thrived in iron and sulfur, rich seas now struggled. But for aerobic life, oxygen-rich shallows became fertile ground. The chemistry of the oceans determined who lived, who died, and who evolved. It was evolution written not only in genes, but in chemistry itself. Imagine drifting across an ancient seascape. Beneath you, stromatolite reefs rise in domes, bubbling oxygen into the water. Fish do not yet exist, nor plants nor animals. But the water is alive with microbes invisible but teeming. In one layer, anaerobes process sulfur. In another, aerobes breathe oxygen. Between them, strange chemical reactions spark, driving cycles of energy. The ocean is not empty. It is a living experiment, one that will last billions of years. Even today, echoes of this ancient chemistry persist. In modern oceans, oxygen levels vary by depth. There are oxygen-rich surfaces, anoxic basins, sulfurous vents. In places like the Black Sea, we see conditions not unlike those of the Proterozoic: oxygen at the top, sulfur, rich waters below, a sharp boundary in between. These modern analogues remind us that the chemistry of the oceans is never static, but always in flux. The slow oxygenation of the oceans also prepared the way for future leaps. By oxidizing iron and sulfur, oxygen altered nutrient cycles in ways that would one day support eukaryotes and multicellular life. It created the conditions for new biochemistry, new adaptations, and ultimately, greater complexity. Without these chemical shifts, the later rise of animals would not have been possible. But in this moment of deep time, the process was still unfolding. Oxygen was spreading, but slowly. The oceans were still layered, still resistant, still rich in the chemistry of their ancient past. Life was adjusting, evolving, experimenting with new strategies. The chemistry of the oceans tells us that revolutions are not sudden. They are layered, gradual, patient. Oxygen did not conquer in a day. It seeped, accumulated, wrestled with iron and sulfur, pushed against the weight of the past. And in that slow process, the foundations of the future were laid. So picture those ancient seas once more. Above, the skies are bluer, clearer than they were in the methane age. Below, the waters ripple with hidden chemistries, rich with iron, sulfur, and oxygen. Microbes drift and multiply, quietly conducting their experiments, balancing between survival and innovation. The oceans are not yet the ones we know, but they are becoming them. And in that becoming, they are carrying life, step by step, molecule by molecule, toward a more complex, oxygenated world. Look up at the sky on a clear day. The sunlight feels warm, golden, gentle. But it is only gentle because our atmosphere protects us. High above the earth, a thin veil of ozone absorbs the harshest rays of the sun, shielding life from ultraviolet radiation. Without it, the surface of our world would be blasted by invisible energy, dangerous and destructive. This protective layer, the ozone layer, did not exist in the early Earth. For billions of years, sunlight streamed down unfiltered, bathing the oceans and continents in ultraviolet light. To us, such conditions would be fatal. DNA unprotected under such radiation breaks apart, cells die, and complex life cannot endure. But in those early times, life existed mostly in the oceans, where water provided a natural shield. The seas were a refuge against the sun's fierce rays. Everything began to change with the rise of oxygen. As cyanobacteria filled the atmosphere with their waste gas, some of that oxygen drifted upward, high into the stratosphere. There, under the influence of sunlight, oxygen molecules all were split apart. The fragments recombined into ozone. And slowly, molecule by molecule, a protective shield began to spread across the planet. It is humbling to think how delicate this process was. Cyanobacteria never intended to build a planetary sunscreen. They were simply surviving, photosynthesizing, releasing oxygen. Yet their byproduct gave rise to ozone, and ozone gave rise to protection. For the first time in Earth's history, the planet's surface began to be safe from ultraviolet assault. Imagine the difference this made. Before ozone, life was confined to the oceans, sheltered beneath waves. The shallowest waters, where sunlight was strongest, could be harsh for exposed cells. But once ozone spread, even surface waters became less dangerous. The intensity of radiation eased, habitats expanded, and in the long course of time, land itself would be opened as a possible home. The ozone layer did not appear suddenly. It formed gradually as oxygen accumulated in the atmosphere. At first, levels were low, the shield weak and patchy, but even a thin veil made a difference. reducing ultraviolet rays just enough to allow more life to survive at the surface. As oxygen levels grew stronger, so too did the ozone. By the end of the Great Oxidation Event, Earth had gained not just breathable air, but a new kind of armor. This armor was transformative. It was the quiet foundation for everything that followed. Without ozone, eukaryotes, the complex cells that would one day evolve into plants and animals, could not have flourished near the surface. Without ozone, the colonization of land would have been impossible. Forests, animals, and eventually humans owe their existence not just to oxygen in the air, but to ozone high above. Even today, we see the importance of this shield. Where ozone thins, as it did in the late 20th century, in the so-called ozone hole over Antarctica, the consequences are immediate. Increased radiation damages crops, harms plankton, and causes cancers in humans. That thin veil, fragile and invisible, remains essential to life's stability, and it all began during the Great Oxidation Event. Geological clues support this story. The appearance of certain sulfur isotopes suggests a shift in atmospheric chemistry consistent with the rise of ozone. Other evidence comes from the biological record itself. The expansion of life into shallower waters corresponds to the timing of oxygen's rise and the protection ozone provided. It is as though Earth's biosphere waited for the sky to grow safer before venturing into brighter realms. The birth of the ozone layer also changed the climate by filtering ultraviolet radiation. Ozone influenced how energy was absorbed and distributed in the atmosphere. It added a new layer of complexity to Earth's climate system, stabilizing temperatures and interactions between air and sunlight. Though subtle at first, these changes laid groundwork for the more stable climates that followed. There is poetry in this process. From the smallest of microbes came oxygen. From oxygen came ozone. From ozone came protection. And from protection came possibility. The possibility of forests, of animals, of humans standing beneath the sun without fear. Imagine watching the sky billions of years ago. At first, the sun blazes harshly, unfiltered, scorching land and sea alike. Then, slowly, the chemistry of the air begins to change. The ultraviolet light splits oxygen, ozone forms, and the harshness eases. The sky does not look different to the eye, but the radiation is gentler. The world feels safer. Life stretches upward, closer to the light. The ozone layer is so thin, if compressed, it would be only a few millimeters thick at the surface. And yet it is enough. A fragile shield, delicate and enduring, born from the quiet labor of microbes. When we look back at the Great Oxidation Event, we often focus on oxygen filling the air, on red beds and iron formations, on extinctions and crises. But just as important was this invisible transformation above. The sky itself became a sanctuary. The Earth gained a new layer of protection, one that would make complexity possible. And so, as cyanobacteria multiplied and oxygen rose, the ozone layer was born. It was not dramatic, not visible, not even noticeable at the time. But in its quiet way, it changed the destiny of the planet. The Earth, once bare beneath a dangerous sun, now wore a veil that softened the light, shielded the fragile, and invited life to grow in new ways. The birth of the ozone layer was not just a chemical event. It was a promise that life could expand, adapt, and one day reach far beyond the seas. Take a deep breath in and slowly let it out. The air you inhale feels calm, balanced, familiar. But that balance, between oxygen, carbon dioxide, and the other gases of our atmosphere, is delicate. It has always been delicate. And during the Great Oxidation Event, the Earth's climate system was learning, for the first time, how to stabilize itself under new conditions. When oxygen began to rise, it reshaped not only life in rocks, but also the planet's climate. For billions of years before, methane and carbon dioxide had done most of the work of keeping Earth warm under a faint young sun. Methane, especially, had been critical, a powerful greenhouse gas exhaled by methanogenic microbes. But oxygen destroyed methane, stripping it away and replacing it with carbon dioxide, a weaker blanket against the cold. This shift caused cooling. We have already seen how it may have triggered snowball Earth episodes, vast glaciations that spread across the continents. But in the long term, the Earth did not remain frozen. Instead, new feedback loops began to stabilize the climate, balancing the roles of oxygen, carbon, and other gases. One of the most important feedbacks was the carbon cycle. Volcanoes belched carbon dioxide into the air, adding greenhouse warmth. Rain driven by oxygen-rich skies reacted with rocks, drawing carbon dioxide back down and locking it away as carbonate minerals. This tug of war, volcanoes adding Kyle, weathering removing it, became a thermostat for the planet. If Earth grew too warm, weathering sped up, pulling more Tao from the air. If Earth grew too cold, weathering slowed, allowing Tao to build again. In this way, the planet began to regulate itself, keeping conditions suitable for liquid water and for life. Oxygen itself contributed to these cycles. By oxidizing minerals, it accelerated the breakdown of rocks, speeding up carbon burial. By altering the chemistry of the oceans, it influenced how carbon was stored in sediments. For the first time, oxygen and carbon were working together in feedback loops that stabilized climate across deep time. These loops were not perfect. They overshot, undershot, triggered ice ages and warm intervals. But they provided a long-term balance that allowed life to continue. Without them, Earth might have swung wildly between extremes, frozen solid or overheated, uninhabitable for billions of years. Instead, the planet settled into rhythm, learning to breathe in carbon and breathe it out again, like the slow pulse of a living organism. Nitrogen, too, played a role. With oxygen present, nitrogen cycles shifted, supporting new microbial metabolisms. These changes influenced productivity in the oceans, which in turn affected how much carbon was buried or released. Every gas, every element, every cycle became linked, woven together into a complex web of feedbacks. Imagine the Earth as a vast, self-regulating system. Volcanoes provide the input, oceans and rocks provide the storage. Life provides the chemistry, and oxygen, new, disruptive, transformative oxygen, ties the pieces together in new ways. This was not just a story of survival, but of stability. The Great Oxidation Event forced the Earth into a new equilibrium, one that would endure for billions of years. Our own existence depends on that equilibrium still. When we talk about climate change today, we are tugging at those ancient feedback loops, altering balances that were first established during this age. The evidence for these stabilizers lies in the rocks and isotopes. Geologists find carbon isotope shifts that show pulses of burial and release, marking the operation of the carbon cycle. They find weathering patterns in ancient soils that reveal how Kl levels fluctuated under oxygen-rich skies. And they trace the timing of glaciations and warm periods, showing the fingerprints of feedbacks at work. It is remarkable to think that microbes, by releasing oxygen, not only poisoned one biosphere and created another, they also nudged the planet into stability. They turned a world ruled by unstable methane into a world buffered by oxygen-carbon feedbacks. They gave Earth the ability to regulate itself more gently, more reliably. There is poetry in this. Life did not just adapt to the planet. Life helped the planet adapt to itself. Oxygen was not only a byproduct of survival, it was a tool that rewrote the relationship between Earth's atmosphere, oceans, and rocks. Picture again the ancient Earth. Glaciers cover parts of the continents, seas pulse with oxygen and iron, skies grow clearer. Beneath it all, cycles turn, volcanoes release carbon, rain scrubs it away. Oxygen quickens the reactions. The planet finds a rhythm, a breath. It was not a perfect rhythm. There were still crises, still mass extinctions, still ages of ice and fire. But the framework had been built, the feedback loops established. From this point onward, Earth had the tools to sustain life in balance. Without these stabilizers, complexity would never have had the chance to emerge. Animals, plants, and humans require long stretches of stability, climates that remain within ranges we can endure. The Great Oxidation Event gave Earth that possibility, by tying oxygen and carbon into a system of checks and balances. When you breathe now, you are part of that ancient loop. You inhale oxygen, you exhale carbon dioxide. Plants and microbes reverse the cycle, taking in carbon, releasing oxygen. It is a dance billions of years old, born in the Great Oxidation Event, still carrying us forward today. Take a slow, deep breath. The oxygen filling your lungs right now is the same element that once transformed the entire planet. It was not just a chemical change in the air. It was an invitation for life to become more than it had ever been before. The Great Oxidation Event, by raising oxygen levels in the atmosphere and oceans, set the stage for the next great leap in evolution, the rise of complex cells known as eukaryotes. These were not the simple, single compartments of bacteria and archaea. They were something new, larger, more intricate, with internal structures that made new possibilities of life imaginable. But to reach this point, life had to endure billions of years of struggle. For much of Earth's history, the biosphere had been microbial. Flat in its diversity, limited by energy, anaerobic metabolisms yielded only modest amounts of energy. Even aerobic bacteria, though efficient, remained small and simple. Complexity was constrained by what cells could do with the energy available to them. Oxygen changed the equation. Through aerobic respiration, cells could extract far more energy from food. Instead of a trickle, they now had a flood. This surplus allowed them to power new structures, new processes, new ways of organizing life. It was like moving from candles to electricity. The possibilities expanded dramatically. The first step toward complexity may have been cooperation. Evidence suggests that eukaryotes arose through a process called endosymbiosis, where one cell engulfed another, and instead of digesting it, the two formed a partnership. The engulfed cell, an aerobic bacterium, became what we now call a mitochondrion, the powerhouse of the cell. By working together, the host cell and its new partner combined resources. The mitochondrion used oxygen to generate vast amounts of energy, which the host cell could then use to grow larger, build more structures, and manage more complex chemistry. Without oxygen, this partnership would have been meaningless. But in the oxygenated world of the GOE, it was revolutionary. The energy mitochondria provided unlocked the door to true complexity. Imagine drifting in the oceans of 1.8 to 2 billion years ago. Most of the world is still microbial, filled with cyanobacteria anaerobes and simple aerobes, but scattered among them are the first eukaryotic cells. Larger, rounder, filled with internal compartments. They move differently, they divide differently, and they carry inside them the legacy of an ancient merger. These cells are the ancestors of all plants, animals, fungi, and us. The GOE did not immediately flood the world with eukaryotes. The oxygen levels were still relatively low compared to today, perhaps only a few % of our modern atmosphere. But even that small rise was enough. It created niches where eukaryotes could survive, thrive, and slowly spread. Over the next billion years, they would diversify, experimenting with new forms and metabolisms. Geological evidence supports this story. Microfossils from rocks about 1.6 to 2 billion years old show larger, more complex shapes than typical bacteria. Chemical signatures hint at the presence of sterols, molecules that only eukaryotes produce. These are the fingerprints of complexity emerging from oxygen's shadow. But the rise of eukaryotes was not rapid. It was slow, hesitant, drawn out over hundreds of millions of years. Oxygen provided the opportunity, but the world was still in flux. Glaciations came and went. Oxygen levels rose and fell. Complex cells had been born, but they had not yet flourished. The stage was set, but the play had only just begun. Still, it is hard to overstate the importance of this transition. Before eukaryotes, life was limited to the microscopic. After them, the path to multicellularity, to tissues, to nervous systems, and eventually to consciousness became possible. Every oak tree, every whale, every human, all of them trace back to this leap, made possible by oxygen. There is something poetic in the idea that oxygen, once a poison, became the enabler of greatness. It wiped out anaerobes, pruned the biosphere, caused mass extinction. But in doing so, it cleared the way for cells that could not only tolerate it but use it. Cells that turned danger into opportunity. Cells that turned waste into power. Picture again one of those first eukaryotic cells. Inside it, tiny mitochondria are at work, consuming oxygen, releasing energy. Around it, the seas ripple with cyanobacteria, still exhaling oxygen into the air. And within the wider world, the feedback loops of oxygen and carbon are stabilizing the climate. It is a fragile balance, but one that allows complexity to survive. From these beginnings, the story of life expands. The GOE did not just make Earth habitable in a new way. It set in motion the rise of everything we recognize as alive today. It made possible forests, oceans filled with fish, skies filled with birds, and minds capable of imagining deep time. All of it began with oxygen and with the partnership between cells that learned to use it. The Great Oxidation Event was not just a crisis. It was not just an extinction. It was also a foundation, a stage upon which complexity could appear, and in the quiet depths of the Proterozoic oceans, that foundation was laid. The first eukaryotes, small and fragile, carried within them the promise of all that was to come. Take a long, slow breath and let it out. The air you just inhaled is filled with oxygen, nearly 1/5 of it. But what if it weren't? What if the Great Oxidation Event had never happened? What if Earth had remained the planet it was for its first 2 billion years? A world without oxygen. To imagine this alternate Earth, we must begin with its skies. Instead of blue, they remain hazy and orange, tinted by methane and carbon dioxide. Sunlight filters weakly through the thick atmosphere, dimming the world below. The protective ozone layer never forms, so ultraviolet radiation rains down unchecked, striking land and sea with harsh energy. On the continents, there are no forests, no grasses, no animals. Only dark volcanic rock, bare and silent, dominates the landscape. The oceans, too, are different. They remain greenish, heavy with dissolved iron, never rusting into the red beds we see today. Anaerobic microbes fill the waters, living off sulfur and methane. Stromatolites still rise in shallow seas, but they are less abundant, never fueling oxygen's rise. There are no fish, no coral reefs, no kelp forests swaying in currents. The oceans are microbial, ancient, and simple. Life in this alternate world remains small. Without oxygen, aerobic respiration never evolves. Cells cannot unlock the abundant energy needed for complexity. Eukaryotes never appear, for their mitochondria, the engines of oxygen use, never come into being. Without eukaryotes, there are no plants, no fungi, no animals. The biosphere remains microbial, flat, and limited, even after billions of years. Perhaps in this world, anaerobic microbes form diverse ecosystems. They cover rocks, flourish in hydrothermal vents, fill sediments with life invisible to the naked eye. Perhaps mats of sulfur bacteria glow faintly in shallow seas, releasing gases into the air. But they remain small. No forests rise, no animals swim or walk or fly. Earth remains a quiet planet, alive but never complex. Climate, too, would be different. Methane remains abundant in the air, keeping the planet warm under a faint young sun. But methane is unstable. It reacts with sunlight and breaks down. In our world, oxygen kept methane in check. Without oxygen, methane may have waxed and waned, causing wild climate swings, sudden freezes, sudden thaws, instability that made long-term habitability uncertain. Perhaps Earth would have frozen solid many times, unable to stabilize its climate. Perhaps life would have endured, but always at the edge of catastrophe. And what of us? In this alternate Earth, humans never appear. The chain of evolution that led to animals, to primates, to consciousness requires oxygen. Our lungs, our brains, our muscles depend on aerobic metabolism. Without oxygen, there is no energy for intelligence, no fuel for culture, no spark for civilization. The Earth would remain a microbial planet, alive, but silent of voices, empty of thought. It is sobering to realize how contingent our existence is. The Great Oxidation Event was not inevitable. It was the outcome of cyanobacteria evolving photosynthesis, of oxygen slowly overcoming the planet's sinks, of feedback loops stabilizing climate. If any of these pieces had failed, the Earth might have remained an anaerobic world forever. Yet, there is also wonder in this thought experiment. An oxygen-free Earth would not be lifeless. It would still be teeming with microbial diversity, hidden from our eyes but thriving in countless niches. Life would adapt, as it always does. It might develop strange chemistries, exotic metabolisms, ecosystems we can hardly imagine, but it would be alien to us, familiar in its persistence, yet utterly foreign in its forms. There are places in our solar system that may resemble this alternate Earth. Mars long ago had water but never enough oxygen to sustain complexity. Europa and Enceladus, icy moons of Jupiter and Saturn, may harbor oceans filled with microbial life, surviving without oxygen beneath thick shells of ice. Even Titan, with its orange haze and methane-rich atmosphere, offers a glimpse of what our world might have been like without the Great Oxidation Event. Looking at these worlds helps us appreciate what makes Earth unique. Our oxygen-rich atmosphere is not just a chemical quirk. It is the signature of life itself, reshaping the planet in ways no other body in the solar system has. Without oxygen, Earth would have been just another microbial world, lost among billions. With oxygen, it became the stage for forests, oceans of fish, skies of birds, and eventually us. So imagine one last time the alternate Earth. Stand on its coastline where waves lap at volcanic rock. The sky glows orange, the air heavy with methane. The oceans are dark, filled with microbial mats, but silent of fish or whales. The continents are barren, untouched by trees. Above, ultraviolet light blazes down unfiltered, scorching the surface. There is no oxygen to breathe, no ozone to shield, no complex life to see. It is still Earth, but not our Earth. A world paused in its microbial youth, never stepping into complexity. A world without oxygen, without eukaryotes, without us. The Great Oxidation Event spared us this fate. By flooding the air with oxygen, it opened the door to everything that followed. Without it, we would not be here to imagine alternate histories. Without it, there would be no imagination at all. Take a steady breath. The oxygen filling your lungs is abundant now, about 21% of the air. But it wasn't always this way. Even after the Great Oxidation Event, oxygen levels did not simply rise smoothly to the levels we enjoy today. Instead, Earth's atmosphere wavered, pulsed, and fluctuated, like a hesitant breath. The GOE was the beginning, but not the end of Earth's oxygen story. After the first great rise around 2.4 billion years ago, oxygen levels remained low by modern standards. They may have hovered only at fractions of a percent, far too little to support animals or plants. The biosphere had taken a step forward, but it was still fragile, still uncertain. The atmosphere, in a sense, inhaled oxygen and then exhaled it again. Geological evidence shows that after the GOE, oxygen levels may have declined for hundreds of millions of years in what scientists sometimes call the oxygen overshoot and crash. The atmosphere spiked, then fell, then stabilized at low levels. Why? Because the Earth's feedbacks were still adjusting. Volcanoes continued to release gases that consumed oxygen. Burial of organic matter was inconsistent. The balance was delicate, and the atmosphere reflected that fragility. Yet even in these fluctuations, life was adapting. Eukaryotes had appeared, complex cells that relied on oxygen for energy. They could survive at low levels, but they needed stability. Each pulse of oxygen provided opportunity, brief windows for complexity to expand. Each crash tested resilience, forcing survival through scarcity. This pattern repeated through Earth's history. There were at least two other major oxygenation events after the GOE. The first was the Neoproterozoic oxygenation event around 800 to 600 million years ago. During this time, oxygen rose again, more substantially than before. It coincided with another round of snowball Earth glaciations, when ice spread across the planet. When the ice retreated, oxygen surged in the atmosphere and oceans. This time, levels may have reached 10% of today's, enough to support large, multicellular organisms. And indeed, this was the age of the Ediacaran biota, Earth's first strange, quilt-like animals. The second great pulse came in the Paleozoic oxygenation event, around 400 to 300 million years ago. Here, oxygen levels rose even higher, perhaps to 30 or 35% of the atmosphere. Forests spread across continents, their roots burying vast amounts of carbon. This burial removed carbon dioxide and allowed oxygen to accumulate. Gigantic dragonflies with wide wingspans took to the skies, their size made possible by the oxygen-rich air. It was a world bursting with energy, fueled by oxygen at its peak. These later pulses were echoes of the first. Without the GOE, they could not have happened. It was the GOE that first shifted Earth into an oxygenated trajectory. It was the GOE that established the feedback loops, the sinks, the cycles, the very chemistry that allowed oxygen to wax and wane. Each later event was a reinforcement, a reminder, a continuation of the story first written by cyanobacteria. The echoes also remind us of oxygen's complexity. It is not a simple gas rising smoothly upward over time. It is a dynamic element tied to life, rocks, oceans, and climate. Its history is jagged, full of rises and falls, crashes and recoveries. It breathes just as we do. Imagine Earth as a living organism. The GOE was its first deep breath, sharp and disruptive. The Neoproterozoic was another, steadier inhalation filling the lungs a little more. The Paleozoic was a great expansion, oxygen surging, the planet exhaling forests and animals in abundance. And today, we live in the rhythm that followed, a balance, a breath, a cycle that sustains us still. The echoes of the GOE also tell us about resilience. Life did not flourish immediately after oxygen first appeared. It took nearly 2 billion years for animals to evolve after the GOE. That delay was not because oxygen was absent, but because oxygen's story is complex, woven with rises and collapses, with crises and opportunities. Complexity required patience. Today, when we look at the record of oxygen, we see its fingerprints in rocks, fossils, isotopes, and even in the shapes of landscapes. Red beds mark its spread on land. Banded iron formations mark its first stirrings in the seas. Coal deposits and giant insects mark its Paleozoic abundance. Each echo is written into the earth itself. It is remarkable to think that all of these later pulses, the rise of the first animals, the spread of forests, the flight of dragonflies, the bloom of fish in the seas, trace back to a beginning more than 2.4 billion years ago, a beginning when tiny cyanobacteria in shallow seas released waste gas into the water. That waste oxygen became destiny. So imagine the echoes as waves. The first wave was the GOE, sudden, powerful, reshaping everything. The second wave in the Neoproterozoic lifted the biosphere again, making room for animals. The third, in the Paleozoic, swelled even higher, fueling forests and giants. And we humans live in the wake of those waves, breathing air that carries the memory of all three. The Great Oxidation Event was not the only oxygenation, but it was the first. It was the root, the foundation, the spark. Without it, the later echoes would never have come. Without it, Earth would have remained silent, microbial, and simple. The echoes of oxygen remind us that life and the planet are never static. They move in cycles, in pulses, in rhythms that span billions of years. And in those rhythms, we find the story of life itself. Take a deep, calm breath. The oxygen flowing into your lungs is invisible, weightless, easy to forget. But it is the thread that connects you to everything around you. The forests, the oceans, the animals, and even the stones of ancient Earth. It is the legacy of an event that began more than 2.4 billion years ago, when tiny microbes first filled the world with a gas no one asked for, no one wanted, and yet one that would become the greatest gift life ever received. The Great Oxidation Event was not a single moment, not a flash of change, but a slow unfolding. It began in shallow seas, with cyanobacteria quietly exhaling oxygen. It spread into the oceans, rusting iron and leaving behind banded iron formations. It spilled into the air, staining rocks into red beds, collapsing methane's greenhouse blanket, and chilling the planet into ice. It poisoned the ancient anaerobes, triggering the first mass extinction. And yet, from all that upheaval, it laid the foundation for complexity. From oxygen came eukaryotes, born from partnerships between cells. From oxygen came the ozone layer, shielding the surface from ultraviolet radiation. From oxygen came climate stabilizers, feedback loops that balanced Earth's breath between carbon and air. And from oxygen came the possibility of animals, forests, and minds that could look back and remember deep time. It is easy to see oxygen as ordinary, because it is everywhere now. But in truth, it is extraordinary. The air you breathe is a planetary monument, built not of stone or steel, but of molecules maintained by life itself. Every breath is history, the echo of cyanobacteria, of ancient oceans, of rocks rusting in silence billions of years ago. Imagine Earth before oxygen, orange skies, green seas, continents bare and lifeless, a planet alive, but microbial, quiet, and simple. Now imagine Earth after oxygen, blue skies, oceans layered with life, continents someday covered in forests. The difference is invisible to the eye, but profound in its consequences. It is the difference between a world of microbes and a world that could one day hold consciousness. The Great Oxidation Event reminds us of the patience of time. It took millions upon millions of years for oxygen to accumulate, for the sinks to fill, for the balance to tip. It was not a revolution overnight, but a slow tide rising unstoppable, shaping the world with every bubble of gas. Change, even planetary change, come quietly, almost unnoticed, until one day everything is different. There is also humility in its story. The greatest transformation in Earth's history was carried out not by giants, not by sudden catastrophes, but by microbes, by cells too small to see, living in mats and colonies, dividing endlessly under the sun. They had no plan, no vision, no awareness of what they were doing. And yet, through persistence, they altered the chemistry of the planet forever. It is a reminder that even the smallest forces, over long enough time, can change the world, we live in the shadow of that transformation. Our lungs, our blood, our cells are tuned to oxygen's rhythm. Our civilizations rise and fall under skies filled with it. And even as we speak, photosynthetic organisms, plants, algae, cyanobacteria, continue the work their ancestors began billions of years ago. They breathe out the oxygen that sustains us, maintaining the balance we depend on. The Great Oxidation Event never truly ended. It continues in every leaf, every plankton bloom, every breath. There is a certain gratitude we might feel when reflecting on this. Not gratitude in the way we thank a person, but a deeper, quieter appreciation for the forces of nature, for the invisible gifts that sustain us. We did not earn oxygen. We did not design it. We inherited it, the result of life reshaping its planet. It is a gift beyond intention, a gift of chemistry, a gift of time. So, as we close this journey, imagine once more the arc of Earth's history, the quiet microbial seas of 3 billion years ago. The oxygen leak, bubbles rising in shallow waters. The red beds, rusted rocks recording the first breaths of air. The collapse of methane, the spread of glaciers, the mass extinction of anaerobes, and the slow rise of aerobes. The birth of eukaryotes, the ozone layer, the stabilizers of climate. The echoes of oxygen in later ages, feeding forests and animals. And finally us, humans, breathing deeply, imagining deep time, telling stories of a world we did not see but that made us possible. The Great Oxidation Event is a story of patience, of crisis, of transformation. It is the story of how life reshaped a planet and how that planet, in turn, reshaped life. It is the story of oxygen, Earth's invisible gift, fragile, powerful, and enduring. So take one last breath with me now, in and out. The air fills your lungs, flows through your blood, sustains your cells. It is the same oxygen born in the ancient seas, the same oxygen that has carried life for billions of years. A gift from microbes, a gift from time, a gift from the earth itself. The Great Oxidation Event was not just important, it was essential. It was the turning point that made our world the world we know.